Galaxies are the building blocks of the universe and the sites of star formation. Inside galaxies, star formation happens in the dense parts of giant molecular clouds. We know that the amount of dense gas is strongly correlated to the rate at which stars form, known as the Gauss-Solomon relation. This relation spans over more than 10 orders of magnitude, from nearby clouds in the Milky Way, over resolved measurements in nearby galaxies, to the distant universe, and suggests a universal picture of star formation across the cosmos. However, recent studies have shown that dense gas alone does not set the star formation rate. Instead, also the environment in which the giant molecular clouds reside and the dynamics of the gas, among other factors, can matter and affect how efficiently dense gas is converted into stars. Within PHANGS, we aim to get a better understanding of star formation and the baryon life cycle in galaxies. This means we want to shed light on how matter and energy are processed within galaxies. To achieve this, we have acquired a huge data set of more than 70 nearby galaxies that have been mapped at high resolution and various wavelengths with state-of-the-art telescopes like ALMA, HST, DATE-SST, and the VLT. All of these data sets are publicly available, so check them out and play with them. With PHANGS ALMA, we mapped many spiral star-forming galaxies in the molecular gas content as traced by the emission of carbon monoxide, or short CO. CO can easily be excited on the cold ISM, making it an excellent tracer of the bulk molecular gas. However, it does not only trace the gas which is related to star formation, that is, the dense gas. Hence, the next logical step is to investigate the denser molecular gas. The most popular tracer of dense gas in other galaxies is emission from another molecule called hydrogen cyanide, or short HCN. This molecule is typically only excited at higher densities, and therefore a commonly used tracer of dense molecular gas in other galaxies. In a simple picture of a molecular cloud, this means that CO emission originates from a large part of the cloud, while HCN emission is coming from the more denser clumps inside the cloud. While CO can be routinely mapped at high resolution nearby galaxies with observatories like ALMA, doing the same with HCN is much more challenging. This is because HCN is typically 10 to 100 times fainter than CO, and thus requires at least 100 times longer integration times to carry out the similar signal-to-noise ratio. Therefore, HCN and in general dense gas tracer observations of nearby galaxies are challenging and sparse. But they are necessary for a deeper understanding of star formation, and thus PHANGS designed a survey to overcome the lack of dense gas maps of galaxies, and we observed 25 of the PHANGS galaxies in HCN and other dense gas tracers. You can see the 25 galaxies here. These observations of these 25 galaxies were carried out over several observing cycles with ALMA and took in total several hundred hours. The survey is called ACA Large Sample Mapping of Nearby Galaxies in Dense Gas, or short ALMOND. And the hook to remember the survey name is that HCN, hydrogen cyanide, the main objective of the survey, actually smells like almonds. But be aware that you should never taste HCN actually, because it's very toxic, so stay safe, be an astronomer, and observe HCN. The fantastic thing about PHANGS is that we have plenty of beautiful observations from different wavelengths and at match resolution for the same galaxies. Therefore, studying different properties and physical mechanisms and comparing them are easy to do. In addition to the dense gas tracers we've mapped with ALMOND, that is HCN, HCO+, and CS, we have ancillary CO data, the trace of the bulk molecular gas, and infrared and UV data to measure the star formation rate. In past studies, it was found that the kiloparsec scale environment affects the properties of giant molecular clouds. Moreover, the connection between the properties of dense gas and star formation with the kiloparsec scale environment has been made. However, before ALMOND, it was not possible to make a connection between the dense gas measurements and the properties of molecular clouds in a significantly large sample of galaxies. This missing link is addressed with the first ALMOND paper that I will talk about in the following. One of the key science questions we wanted to address with the ALMOND survey was whether the properties of dense gas and its ability to form stars depend on the properties of molecular clouds, and if these connections are consistent with expectations from theoretical models. In a more simplistic way, we can describe a molecular cloud as a spherical object with a radial density profile so that the gas becomes denser towards the inner parts of the cloud. In this molecular cloud model, CO will trace most of the cloud, while HCN is tracing denser parts. Star formation will happen in the inner clumps of the cloud that reach densities high enough to collapse under their own gravity. In this work, we measure two quantities related to the dense gas content. First, we approximate the dense gas fraction via the HCN to CO line ratio. And second, we measure the star formation efficiency of the dense gas via the ratio of the star formation rate to the HCN line intensity. From the PHANGS CO data, we infer properties of giant molecular clouds, such as the surface density, is the mass per unit area, from the integration intensity, and the turbulence or velocity dispersion from the line width of the CO spectrum. With these measurements, we can quantify how dense the molecular gas are on average and how turbulent the molecular gas is. We employ these measurements to all 25 galaxies and compare the dense gas fraction, here on the y-axis, with the cloud properties, here on the x-axis in the two panels. You can see that the dense gas fraction increases systematically with both the cloud surface density and velocity dispersion. This means that high surface density, high turbulence clouds tend to have higher dense gas fraction. We can try to understand these relations from the perspective of the simple molecular cloud model introduced earlier. Based on this model, which assumes a self-gravitating cloud, we can analytically infer its density distribution, which is the first order, well described by a log normal distribution, shown as the white solid line in the right panel. We call this function the probability distribution function, or short PDF. From this model, we can predict the parts of the density distribution function that emit in CO or HCN, as well as the overdense part that is collapsing to eventually form stars. Let's first focus on the emission of CO and HCN that we utilize to measure the dense gas fraction. In this model, we can vary the parameters of the cloud, for example the mean density, which is related to the surface density of the cloud, and moves the density PDF from left to right. We can see that by moving the PDF to higher mean densities, we get a larger fraction of gas that can emit in HCN relative to CO, and thus a higher dense gas fraction. Similarly, we can vary the turbulence in the cloud and find that increasing the turbulence also increases the dense gas fraction. This is because increasing the turbulence widens the PDF, which results in more gas at lower densities, but also more gas at higher densities. Hence, the increase in the HCN emission relative to CO. Therefore, the observed positive correlation can be well understood via the perspective of turbulent cloud models. Next, we have a look at the star formation efficiency of the dense gas. That's traced by the star formation rate per HCN line intensity. Again, here shown on the y-axis and the cloud properties on the x-axis. We employ the same analysis as before over all 25 ALMOND galaxies, and in this case we find a negative correlation between the dense gas star formation efficiency and the cloud properties. The negative correlation is significant, but has a larger scatter than the relation with the dense gas fraction, pointing towards other factors at play in regulating the star formation. Again, we try to understand the relations and the underlying physics from the cloud model perspective. This time we focus on the HCN emitting gas and the star forming gas. The latter is analytically inferred from the Jeans criterion, which defines the critical mass above which a self-gravitating object will collapse under its own gravity. Let's first look at the effect of varying the cloud turbulence. Like before, the PDF gets wider with increasing turbulence, which results in more gas at higher densities and thus more gas emitting in HCN. At the same time, the critical density of gravitational collapse is moving to higher densities, because you need a higher density to counteract the increased turbulence in order for the gas to collapse. And therefore, increasing the turbulence will lower the star formation rate and increase HCN emission, hence decreasing the dense gas star formation efficiency. What happens when we change the mean density is a bit less obvious. Like before, we get more HCN emission at higher mean densities. However, at high densities, also the star formation rate increases, because gas at higher densities collapses faster. Thus, the same amount of collapsing gas can lead to more stars being formed per unit time, which might lead to an increase in the star formation efficiency of the dense gas, especially at higher mean densities. However, in reality, most massive clouds are actually also more turbulent. And so combining the simultaneous variations of turbulence and density, we might actually expect an overall negative correlation between the mean density and the dense gas star formation efficiency, because the turbulence might then eventually drive the star formation at high densities also for variations with the mean density. So overall, we find that dense gas fraction increases, while the dense gas star formation efficiency decreases with the surface density and turbulence of the molecular clouds, in agreement with the model predictions. One interpretation of these results is that in high density, high turbulence clouds, HCN, and this is also true for other dense gas tracers, are not tracing the overdense gas anymore that is forming stars, but become traces of the overall bulk molecular gas, similar to CO in the lower density regime. Another main result of this work is that gas turbulence is a key driver in regulating star formation and the formation of dense gas. In summary, with the ALMOND survey, we mapped 25 nearby galaxies and dense gas tracers such as HCN, but also HCO+ and CS. We used these data to show that the fraction of dense gas and the star formation efficiency of the dense gas is systematically varying with the properties of giant molecular clouds that we have from the PHANGS ALMOND survey, such as the density or the turbulence. So that we now have found the missing link between dense gas and star formation and the cloud properties. Thus, we have found a coherent connection between dense gas tracers, star formation, and the properties of molecular clouds in agreement with predictions from turbulent cloud models. The logical picture that arises now within galaxies is that the kiloparsec scale environment affects the properties of individual giant molecular clouds, which in return affect how much of the gas in these clouds is dense and how efficiently dense gas can be converted into stars, with the key driver being the gas turbulence.